Hello everybody! In this clip we determine the orbit decomposition of an affine toric variety arising from a lattice core. We begin with a simple example. Look at the cone sigma generated by 1, 0 and 0, 1 in Z2. So here's our sigma. Besides itself, sigma has two one-dimensional faces, the ray rho 1, the ray rho 2, and it has a zero-dimensional face, the origin. Our aim is to determine in a systematic manner the orbit decomposition of the associated toric variety X sigma, which is just C2 in this case. The key to the orbit decomposition are the limit points of one-parameter subgroups. So, for a vector v equal v1, v2 from Z2, we have to look at the limit t goes to 0 of lambda v of t applied to x naught, which concretely means we look at the limit of t goes to 0, t to the v1, t to the v2. We know already what happens in this case. In order that this limit exists, we need v1, v2 both to be greater or equal to 0, and we will end up with four possible limit points: the origin 1, 0, 0, 1 and the base point x naught of our toric variety. However, let us look at this in a systematic manner. Here are all the possibilities. This is our one-parameter subgroup lambda v, and here is the associated limit point. In order that we get the origin as a limit point, we need that v1 and v2 both are strictly bigger than 0. That means our vector v comes from the relative interior of our cone sigma. Similarly, if we want to reach the limit point 0, 1, we need that v1 is strictly bigger than 0 and v2 equals 0. So our vector v must come from the relative interior of the first ray. That means any vector in the ray, but not the 0 vector. The same with the other cases. For rho 2 we end up with 1, 0, and for the 0 cone we end up with a base point x naught. Summarizing, that means that the faces of sigma are in a one-to-one correspondence with the limit points of x sigma. Moreover, the torus orbits through these limit points, they cover in a disjoint manner our x sigma. That means we have found the orbit decomposition. Just the torus orbits through the limit points x tau, where tau is a face of sigma. Before we can treat the general case, we have to get prepared a bit. First, in our constructions, we start with a lattice n in general. At some point pass to the dual lattice M. What we want is to regard n and m as dual to each other. That means we need a bilinear pairing. This is defined as follows. For a linear form u in n and a vector v in n, we define this bracket as linear form u applied to the vector v. Once we have this bracket, we define vector v applied to linear form u to be this bracket. The second thing are characters and one-parameter subgroups of the torus Tn associated with the lattice n. We know that the character group is isomorphic to m via sending an element u of m to the character chi u. And we know that the lattice of one parameter subgroups is isomorphic to the starting lattice n via sending a vector v to the one parameter subgroup lambda v. This lambda v is a homomorphism from C star to Tn defined by the homomorphism of lattices from Z to N sending 1 to V. In this context, the bilinear pairing of characters of Tn and one parameter subgroups of Tn is just given by the bilinear pairing defined above. Next, we have to take a look at the functions of the affine toric variety x sigma arising from a lattice cone sigma. X sigma was defined to be the spectrum of the monoid algebra. So the algebra of functions of x sigma is this monoid algebra, generated as a vector space by the character functions Ku, where u stems from sigma dual intersected n. Important for us is that these character functions Ku from x sigma are homogeneous with respect to the torus action. That means the following. If we evaluate Ku at a point t dot x, then the result should be Ku applied to t times Ku applied to x. Why this is true? This here is just the pullback of the character with respect to the action map. The action map was defined via its comorphism sending Ku to Ku tensor Ku. So we have to apply Ku tensor Ku to the pair Tx, and the result is exactly what we have. We also need some convex geometry. First, the relative interior of a cone. In general, a cone sigma in a vector space in Q need not be of full dimension, so it will have no interior points. That's why we take the relative interior. This is defined as a set of interior points of sigma with respect to the linear subspace generated by sigma. There are two obvious observations on the relative interior. The first is, if I remove the relative interior from a cone, what is left is the relative boundary, and this relative boundary is the union over all the proper faces of sigma. The next is that the cone sigma is a disjoint union over all the relative interiors of its faces. The second thing from convex geometry is the face correspondence of a cone and its dual. That means we have a bijection from the set of faces of sigma to the set of faces of sigma dual, sending a face to the perpendicular space to tau intersected with sigma dual, and the inverse of this map from here to there is defined in an analogous manner. Important for us is the following observation. If you have a face tau of sigma and a vector v from the relative interior of tau, then the linear form from sigma dual evaluate as follows on this vector v. We have u applied to v equals 0 if u stems from the perpendicular space. That's clear. We have u applied to v strictly bigger than 0 if it does not come from this perpendicular space. At this point, we use that the vector v comes from the relative interior of tau. We are ready to discuss limit points. So we look at the toric variety x sigma t and x naught defined by a lattice cone sigma in N. The idea is to get these limit points via the character functions on X sigma. X sigma is an affine variety. Its function algebra is generated by the character functions, though these functions should know everything. For the limit procedure, we have to look at lambda v of t applied to the base point x naught. What is the value of a character function chi u on this? First, we use that chi u is t homogeneous, so we can compute this as chi u of lambda v of t times chi u of x naught. Chi u of x naught, by definition of the base point, equals 1. Chi u of lambda v of t is just a bilinear pairing, so this is t to uv in bracket. So, in order that a one parameter subgroup lambda v converges, we need that all these exponents are non-negative. So uv greater or equal to 0 for all the cones used from the dual cone. That means that our v stems from the dual of the dual cone sigma v. This is again sigma. So lambda v converges if and only if our v comes from the cone sigma. Now we know that the cone sigma is a disjoint union over all relative interiors of the faces. Given the vector v in the relative interior of a face, we can evaluate also the character functions on this limit point x tau. Namely, using that observation, we see that chi u evaluates to 1 if u stems from the perpendicular space and to 0 otherwise. So we have found all possible limit points. We have seen that they correspond to the faces, and we have characterized them via the evaluations of the characters on the limit points x tau. Okay, so far we know the limit points. At the end we want to have the orbit decomposition. So what is still missing is that every orbit indeed passes through a limit point. For this, the following helps. Consider an affine toric variety defined by a lattice cone and a point inside this toric variety. Then the orbit cone of this point is the cone generated by all u, such that the corresponding character function has a non-zero value at x. This turns out to be a face of the dual cone of sigma. Moreover, we can write down the vanishing ideal of the torus orbit through our x in the algebra of function. The first thing is to realize that this vanishing ideal is generated by character functions, those who vanish on x. And the second thing is to see that these are the character functions where u stems from sigma dual but is not in the orbit cone. Then finally, this ideal turns out to be the vanishing ideal of a torus orbit through a limit point, namely the limit point x tau, where tau is the phase of sigma corresponding to the phase omega x of sigma dual. Summarizing all this, we arrive at the final theorem about the orbit correspondence of an affine toric variety given by a lattice cone. We have mutually inverse bijections from the set of faces of sigma to the torus orbits of x sigma. A face is sent to the orbit through its limit point, and a torus orbit is sent to the face of sigma corresponding to the orbit core. This correspondence is order reversing in the following sense. If we have two faces, tau and tau prime of sigma, then tau is a face of tau prime if and only if the torus orbit through x tau prime is contained in the closure of the torus orbit through x tau. See you in the next clip.